Number systems, table and conversions. I am Engineer James Francis Aguilar and welcome to Computer Fundamentals. Number systems are systems in mathematics that are used to express numbers in various forms and are understood by computers. We have four basic number systems, namely the decimal, the binary, the octal, and the hexadecimal. The decimal is the base 10, the binary is the base 2, the octal is the base 8, and the hexadecimal is the base 16. Their bases represents its digits. For the tables of the number systems, we have here the decimal, binary, octal, and the hexadecimal. For the decimal, which is the base 10, it is composed of 10 digits, which are the 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. While the binary, which is the base 2, we have only 0 and 1, and a combination of that. For the octal number system, we have the 8 digits. We have 0, 1, 2, 3, 4, 5, 6, and 7. We don't have 8 and 9 in octal number systems. For hexadecimal number system, we have 16 digits, which are the 0 to 9 plus a letter which is A, B, C, D, E, and F, which is also the additional 6 number system. Conversions. First, we have the hexadecimal to binary. Example number 1. The given is 3CF, and we have the base 16 to express that the given number system is in hexadecimal. And for the conversions, we have the base number 2 to express that the output is in binary. Looking back at the table, we have here the following conversions. For F, we have 1, 1, 1, 1. Next, we have C, and we have 3. In converting a number system, always start with the rightmost digit going to the leftmost digit. So we have now for F, which is 1, 1, 1, 1. Then for C, we have 1, 1, 0, 0. And for 3, we have 0, 0, 1, 1. If you're going to write that, you will have now 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. Combine that, so you will have the output which is in decimal, in binary. You can also remove the 0 here since it doesn't have a value. Example number 2. We have here a 4-digit which is A0CF. Again, it is also in hexadecimal number system to be converted to binary number system. We have here the table for our reference. Then we start with the rightmost digit, which is F, followed by C, followed by 0, and followed by A. For F, again we have 1, 1, 1, 1. Then for C, we have this one, which is 1, 1, 0, 0. Then for 0, we have a 4-digit 0. Then last, we have A, which is 1, 0, 1, 0. And these are now our digits, which are 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, and 1, 1, 1, 1. Combine that, and we'll have now the answer in binary digit. I intentionally changed the color of the different number system to express that it came from the different individual digits. Next conversions, we have the reverse, which is the binary to hexadecimal. Example number 1. This is the given. You have 1, 1, 1, 0, 0, 1, 1, 1, 1. And the subscript is, or the base is 2 to express that the given number system is in binary, to be converted to the base number 16, which is in hexadecimal. First is, we're going to group it into 4 until to the last digit on the left. We start with the right, followed by the next one, until we have only the remaining digits on the left. For the first one, we have here the first 4 digit in binary, then the second one, which is 1100, then we have here the last or the remaining digit on the left. The first one is this. You have F, which is also equal to 1111. Then the next one is 1100, which is also equal to C. Then the digit on the left is equal to 1. So the answer for the given, which is 11100, 1111, is equal to 1CF. Always take note of the order. Let's have another example for binary and hexadecimal conversion. We have here 1 1 0 0 0 0 0 0 0 and 1, and the given digit having a base of 2, which is binary, and to be converted to a base of 16, which is hexadecimal. Again, let's group it by 4, starting from the rightmost digit going to the left until you have only the remaining digits. The first one is you have 0001, which is also equal to 1. Then the next one is 0000, which is equal to 0. Then the last one, which is 11, which is also equal to 0011, since we do not have the 0, which is also equal to the given, which is 3. So our given number system, the converted number system, is now 301. So we have another conversion. So this time we have hexadecimal to decimal conversions. Example number 1. So the given is 180, given in the base 16 is equal to blank to the base 10. So I have here the equivalent of hexadecimal to the decimal number system. If you're given A, that means in decimal, that is 10. If B, that is 11. C is 12, D is 13, E is 14, and F is 15. The rest, from 1 to 9, hexadecimal and decimal are equal. First is we're going to extract the digit, again from right going to the left. First, obtain B, get the equivalent of that, which is 11, then multiply it by 16, having the exponent 0 is equal to 11. Then get again the next one, A. A is 10 in decimal. Multiply it by 16. This time the exponent now is 1. Then getting the product of this one, we will have 160. 1 in decimal is also equal to 1. Multiply it by 16, and this time the exponent is 2. If you can observe, the exponent is increasing from 0 until to the last digit. Then going back here, you have 1 times 16 raised to 2 is equal to 256. Getting the sum of the product, we have now 427, and that means 1AB in hexadecimal is equal to 427 in decimal. Okay, so let's have another example for hex to decimal, and this time we have now 4 digits, that is FF90, 16 going to the base 10. So we extract the digit, we start from the right going to the left. We get first 0, And even if it is 0, still you have to multiply it by 16 and get the product. Then again, 9 times 16. The exponent now is 1. Get f. What is f in decimal? That is 15. Then multiply it by 16 raised to 2. Then followed by another f, which is also equal to 15 times 16. And this time you have now 3. Getting the product of each, we have 0. 9 times 16 raised to 1, we have 144. The next one is 3840. And the digit on the left, we have 61,440. Adding the product, we will have now 65424. And that will be our conversions. Okay, next we have the decimal to hexadecimal. So this is what quite procedural. So we have example number 1. So the given is 427 given in decimal. As you can see at the base, you have 10 is equal to converted to 16, or the base 16. Okay, the first step is to divide it by 16. Okay, so 427 divided by 16, we can get a quotient which is 26, but it is not exact. We have also 26.6875, and multiply it by 16. So that's the second step. We can get 11, but 11 is still, that is in decimal. To obtain the hexadecimal of that, you have to convert it to B. So 11 in decimal is equal to B in hex. So I will mark it as color red as our indicator for conversions. The next step is get or obtain the whole number, which is 26, then divide it by 16 again. We will get a quotient of 1.625. Again, the 0.625 will be multiplied to 16. We will get a product of 10. Again, 10 is in decimal. Obtain the equivalent of that in hex. We will have 8. Then I mark it as green. The next we will have 1, but 1 is less than 16, so no need to divide it because we'll just obtain 1 if we're going to follow these steps. We will have now 1, and that will be our marked yellow. So why I have marked that? Because of the arrangement. So you're going to write the arrangement from red to yellow. So red followed by green and followed by yellow. So starting from the right, so you will have now 1 AB. So I have here another example. So we have example number 2 for decimal to hexadecimal conversions. And this time we have a longer or a 5 digits decimal to be converted to hexadecimal. So again, first step is to divide it by 16. 65424 divided by 16, we have 4089. But it is perfect, but still we have to express the decimal digit, which is 0.0. Multiply it by 16, then we will going to have 0. In decimal and in hexadecimal, 0 is equal to 0. Then again, the next step. But before that, I mark it again as red. Then next is we have 4089. So I bring it down, then divide it again by 16. I'll get a quotient of 255. That is 255.5625. You can use your calculator to verify it. Then multiply it by 16. We have the product, which is 9, and it is 9 also in hexadecimal. I mark it as the blue indicator. Then next is 255. So I divide it again by 16. I get a quotient of 15.9375. So 0.9375 multiplied by 16, we have 15. But 15, that is in decimal. In hex, that is equal to F. Okay, so I mark it yellow. Then for the last step, we have here 15. And if you notice, 15 is less than 16, so no need to divide it. So, but 15, that is in decimal. We're going to convert it again to hex, so that is F. So this is our indicator. So the indicators start from red, followed by blue, followed by yellow, and followed by green. So that is how you're going to write your converted digits. So the final answer for that is FF90. Okay. So our next number system is binary to decimal. For binary to decimal, so we have here example number 1. So the base is 2. Okay, so we have 1111 to the base 2 is equal to blank 10. So again, we're going to extract the digit again from right to left, going to the left. Okay, so I have the 4 digit here, then I will going to multiply it, and this time 2, and again exponent is from 0 and increasing order. So we have 1 times 2 raised to 0, then we have also another one here times 2 raised to 1, then another one times 2 raised to 2, then another one times 2 raised to 3. Then getting the product of that, we have 1 for the first one, then 2 for the first 2, then 4, then we have 8. And if we're going to add that, so get the sum of the product, we have 15. And also it proved the table that 1111 is equal to 15 and decimal. So if we're going to check for the table, we have here that the given decimal in 15 is also equal to 1111 in binary. Okay, so we have also another example for binary and decimal. We have example number 2. So this time we have 5 digit, which is 10001 in base 2 is equal to blank 10. Okay, so again, we're going to extract the digit and we're going to convert it. So all conversion is from right going to the left. Okay, so we have 1 times 2 raised to 0, followed by the 0 times 2 raised to 1, then 0 times 2 raised to 2, 0 times 2 raised to 3, and we have 1 times 2 raised to 4. Okay, so even though, so my advice is, even though you have 0 digits, you must follow this step so you will not get a wrong answer. Okay, so the first computation is we have 1, 0 times any number is 0, so we have here 3 zeros, and for the last one you have 1 times 2 raised to 4, so we have 16. Then getting the sum of the product, we have 17. So that's our converted digit. So 10001 in binary is equal to 17 in decimal. Okay, next we have the reverse, which is the decimal to binary. So we have here example number 1. So the given is 12 and the base is 10. To express that the given is in decimal is equal now to blank 2. So that means base 2, we're going to convert it to binary. Okay, so if we're going to look at the table, 12 is 1100 in binary. So we have that on the table. So we're going to prove it if it is true. So first step is to divide it by 2. You will have 6, and since 12 is exactly divisible by 2, we will get a remainder, which is 0. Okay, so I encircle that because that is our first digit. I marked it as our first digit. The next is we have 6, which is this one. Again, divided by 2, we'll have 3 for the quotient. And 6 also, if we're going to divide it by 2, we don't have a remainder. So I encircle that. Then next is we have the 3. So 3 divided by 2, if we're going to proceed to long division, you will have 1. But this time you will have a remainder of 1. The next is we have 1, and 1 is less than to 2. So no need to divide that, since we will go back to the same step. Okay, so we have here as the last operation, which is R1. So I encircle that also, since this is important to our conversions. Okay, so I mark this digit as red, blue, yellow, and 1 to express our writing. So this is the order of writing. So you will start from the 0 here, followed by 0, 1, and 1. So going here. So you will have now the converted digit, which is 1100, and that is also equal to our table. So we have also here a example number 2, which is 15 decimal to be converted to binary. So 15 divided by 2, we have 7. So that is the first step. But 15 divided by 2, that is not exact. So we will have a remainder, which is 1. Then I mark it red. Then followed by 7 divided by 2, we'll have 3. Then 3, also we have a remainder, since 7 is not exactly divisible by 2. So you will have a remainder, which is also 1. Then I mark it blue. The next is 3 divided by 2. So we have 1, then we have a remainder for that, which is also 1. Okay, so I mark it yellow. Okay, so we have now Last digit is 1. We do not need to divide it since 1 is less than 2. So I mark it this one as green. Okay, so we have now red, the blue, and yellow, and green. So you're going to write it in this way. Okay, so if we're going to solve this one, so since we have a answer which is all 1, so we our order will not going to affect our writing. But if you have a different digit, so this is very important. Okay, so always follow the order. So this number 1 here is equivalent to this number 1 here. Okay, and this number 1 here is equivalent to number 1 on your left. And also it proved the table that we have 15 in decimal is equal to 1111. Okay, so next is we have octal to decimal. Take note that octal have only 8 digits while decimal is 10. So example number 1, we have 777 and the given is an octal. Okay, so we do not have 8 and 9 in octal, so you must not encounter that kind of number system. If you're going to encounter a number system having 8 and 9 in octal, that means it is a wrong number system. Okay, so again, we're going to extract it and we're going to compute from right going to the left. So we have 7 times 8, and this time we have 8 as the multiplier, and also it's resembled on what is the base given. Again, our exponents start from 0, and then we will have a product which is 7, then followed by another 7 multiplied by 8 raised to 1, then you will have 56. Then the last 7 on your left, you will have now 7 times 8 raised to 2, then the quotient or the product is 448. Adding or getting the sum of the product, we'll have now 511. So that means that 777 in octal is equal to 511 in decimal. Okay, so we have another example. So this time we have 4 digits. So again, get the digit. Start from the right going to the left. So we have 5 times 8 raised to 0, followed by 1 times 8 raised to 1, followed by 1 times 8 raised to 2, then followed by 1 times 8 raised to 3. Okay, so once you get the product and add that or get the sum, so you will have now 589. So that means that 1115 in octal is equal to 589 in decimal. Okay, next is we have a decimal to octal number system. It is the reverse of the previous slide. So this is our example number 1. So we have 589. So this time that is the given, and we're going to convert it to octal number system. So again, our step is to divide it by 8. So 589 divided by 8, we will have 73.625. So this time we're going to multiply 0.625 by 8. So we're going to extract only the whole number. Then you will have 5. And followed by the 73 here. 73 divided by 8. So you will have 9.125 times 8. Then the product is 1. So for the first one, I mark it red, and the next one is I mark it again blue for the order of writing. So that is now our converted octal. And we have also 9, since it is greater than 8, so we have to divide it again. So the quotient is 1.125, then multiply it by 8, we'll have another 1 here. So I mark it yellow for the second one. Then we have here the last digit, which is 1, so that is less than 8, so no need to divide it, but still we have to extract that digit, so I mark it green. So don't forget the order of writing, so we will have now 1115. So that is the converted octal digits. Okay, so we have another example. So this time we have 400 given in decimal to be converted to octal. Okay, so 400 divided by 8, so the answer is 50. But it is exactly divisible by 8, but we need the 0.0. So we multiply it by 8, we will have 0. So I mark it as our first digit on the right, then proceed to the next step. We have 50 divided by 8, we will have 6.25. So 0.25 times 8, we will have 2. So I mark it blue for our next digit. Then 6 now is less than 8, so no need to divide it. So we're going to get 6 as our last digit on the left. So you will have now mark it green. So I marked the indicator on how you're going to write it. So you will have now 620. So 400 in decimal is equal to 620 in octal. Okay, so next is we have octal to binary. So for octal to binary, we have here an example number 1. So the given is 710 in octal as expressed for as express of the base, which is 8, is equal to blank to binary. But take a look at first the table. So in converting an octal, so we have here the octal number system, and this is our binary number system. But in converting octal to binary, are going to disregard all the zero. So we need only the 3 digits from the right. Okay, so first is we will have the 0. So again, it is always from right going to the left. 0 is equal to 0, 0, 0. So we need a 3 digit here. Then followed by 1. So 1 is 0, 0, 1. So as I underline from the given table, so you have now 0, 0, 1. Then for the 7, we have 1, 1, 1. So that is the last, which is also here. So you have now 1, 1, 1. So join that given number system. So we have now 1, 1, 1, 0, 0, 1, then 0, 0, 0. So that is our converted binary digits. Okay, so we have another table here. So we have example number 2. So this time we have 4 digits. So again, it is in octal going to binary. Okay, so I extract this digit from the right going to the left. Okay, so we have here 5. So we have 1, 0, 1. Then we have 0, 3 digit 0. Another 0 is another 3 digit 0. Then we have 1. So we have this one, 0, 0, 1. So we have 0, 0, 1. Combine the digit, we will have now 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1. But again, you can always disregard the 0 on the left since it has no value. Okay, then we have also binary to octal. Since it is from binary now and going to octal, the grouping here is from given is from 3 digits only. You do not need to group it by 4, unlike the hexadecimal to binary. Okay, so this is the given 111 001 00. So group it by 3. Okay, so obtain the equivalent for 000, which is also equal to 0, while 001 is also equal to 1. Then the 111, if you can see the table, you have there 7. So let's have another example for that. But by the way, we have the answer for that is 710. Okay, so next one. So we have here the answer. So this is the example number 2. So this is the answer. So we have to prove it. So that the given is 11111 010. So in grouping, so always start with here from the right going to the left. So anything that is left, so you have to take a look at the converted digit or the equivalent digit from here. So we have 010, so this one, so this is equal to 010, that is 2, and 111 is 7, and the last one, this is 11, this is also equal to this one. So we just disregard the 0 here, that is 3. Okay, so we have now 372. So that's the answer for binary to octal. And for hexadecimal to octal number system, we don't have a exact conversion for this one. It will always undergo, it will be always be converted to binary. Okay, so this is the step. First is convert hex to binary, then the converted binary to octal. So that's how we convert hexadecimal to octal. Okay, so for example, the given is AA, so AA. So A is 1010 in binary, another A is 1010, and this time you're going to convert it to octal. So that means you're going to group it by 3. Then 010 is 2, then 101 is 5, then another 10 is 2. So that's how we convert hexadecimal to octal. Okay, So another one is this, yung octal to hexadecimal. So this step is convert the binary, then the converted binary to hex. So for example, this is the given, so we just reverse the process, yung the first one, which is the hex to octal. So we have now 252, then convert it to binary, you have 010, then 5 is 101, then 2 is 010, then now convert it to hex. In converting hex, just remember that you're going to group it into 4. So you have 1010, which is A, and another 1010 is A. So you have another digit on the left, which is 0. So that is also it has no value. So you will have now 0 also. So that is now the conversion from octal to hexadecimal. Okay, so that's it. So that's our conversion. So thank you for watching.